right.
All right,
Hello,
everyone.
everybody. Welcome to another OpenHW Foundation webinar. This one's real special for me because I get to introduce a couple of my heroes, and I'm not making that up. We've got Dr. David Harris and Dr. Rose Thompson with us today, and we're talking about RISC-V System-on-Chip Design. This is a recently published textbook that you can buy. I have my very own coveted copy with me. I can tell you that this is a great text. Also, if you're in attendance at up till the end of this webinar, you'll be automatically entered into a draw for your very own copy. And if you don't win, you're going to want to buy it anyway. It's a pretty good price, and it's just chock full of information. I'm going to hand the baton over to Rose shortly. Rose is going to walk us through a short presentation, giving you a little bit of background and explaining what the textbook's all about and its context. And then we will, once that wraps up, we will get into a Q&A session. I've got some questions queued up for Drs. Harris and Thompson. I also encourage you, if you've got any questions, put them in the Q&A session. There's a button on your far right-hand side. It's got a little question mark in the icon. It's for Q&A. Pretty straightforward. Enter your question there, and we'll read those questions out to Drs. Harris and Thompson at the end of Rose's presentation. Speaking of Rose's presentation, let's get on to that right now. I'm going to hand it over to you, Rose, and we'll see you on the other side.
All right. Hi, everyone. This is going to be a short introduction to what this textbook is all about and sort of the motivations behind it and the accompanying RISC-V processor that is attached to this RISC-V System-on-Chip Design textbook. There are 4 authors for this textbook: David Harris, my PhD advisor, James Stein, myself, and Sarah Harris. This was a big, long textbook for us to write. There's a lot of years of effort that went into this, and we're quite proud of all the work that went into this. And so one of the motivating efforts to drive this textbook is there's this lots of good textbooks out there that explain computer architecture, go through a lot of the theory, give you a lot of good data for why we do certain things in computer architecture education. But there's this disconnect between that theory and all of the history behind where we got to that theory and actually doing a real-world implementation of a CPU and an SoC. And so the purpose of this textbook and the Wally CPU that comes with the textbook is to bridge the gap between the theory and that implementation. And one of the key things we wanted to do with this CPU was we didn't want it to just be a simple teaching processor. You know, there are so many of those out there where it's just a really basic 5-stage pipeline CPU that can do a very minimal set of tasks. We wanted this to be something that could actually be used in a company's product. We wanted this to be something that could be very configurable all the way down from that little education processor, and you can build it all the way up into a fully featured applications processor that can run an operating system. And so the textbook really aims to try and bridge that gap. So it documents the history, the theory about why we're doing a particular implementation style, and then actually does go through the implementation. And very importantly, there is a diagram that matches up with every single module in the RTL. So the key idea behind this textbook is every single chapter builds up piece by piece by piece to get you to that final fully applications processor that can boot a Linux operating system and run user applications. So outline for this short presentation: what is Wally, codenamed, or Wally is the code name. CVW, CORE-V Wally, is the official name in the repository, and then we'll talk about the textbook. This icon here, this is the Harvey Mudd Wally mascot. And then down below here are the logos for all of the universities that were involved in the RTL development. And later on, I'll get involved with some of the other universities and companies that were involved in other aspects of Wally. So Wally is your classic 5-stage pipeline CPU. So it has your instruction fetch, decode, execute, memory, and write back. But it is so much more than that one that you learned in your Introduction to Computer Architecture class. You know, it starts out with your very basic integer instruction execution core, and then it moves on building piece by piece to a fully applications processor. And importantly, it's a configurable processor. So the RTL is designed in such a way that you can specify, do you want to have a microcontroller that strips out the caches, strips out virtual memory, or do you want to have an applications processor that adds back in those features? And there are just hundreds of configuration parameters inside the core. The entire project is available for free on the the URL is Open Hardware Group. They have a new name now, but the URL is github/openhardwaregroup/cbw. All right, so I mentioned this core is a configurable processor, and to help aid in selecting a configuration, we provide 6 standard configurations. The first is what we're calling an embedded core. This is the RV32I configuration. So this has RV32, so it's a 32-bit processor, but this is the embedded version. So there's only 16 CPU registers, and it strips it down to the barest bone CPU. So this will be the smallest implementation for the tiniest possible core you could implement. And from there, we build up larger and larger cores with more features. So there's the simple CPU, RV32I. This is the one you would use when you're introducing computer architecture concepts in a class. And then a microcontroller, which adds integer multiplication and compressed instructions, and a few other features like buses and peripherals. And then an applications core, so a 32-bit apps core that adds caches, branch prediction, virtual memory, and MMUs, and a whole bunch of other really important features. And of course, the 64-bit versions of those 2 processors. When we say that Wally is configurable, we really mean it. That Wally implements a huge number of the available extensions. In fact, from the major list of extensions that Wally doesn't support, there's really only 3 major things that are missing, which are debug, vector, and hypervisor. And we actually have plans in the future to implement these. These are not present in the textbook, but we have plans to do a volume 2, so that may be coming out in the future. But as of right now, the textbook documents how we implement atomics, and we explain what the value of atomics are. We talk about compressed, integer multiply and divide, the embedded extension, all of the floating point precisions, half, single, double, and quad. The floating point chapters. There's the chapter 16 goes through the theory of floating point, and then Appendix F goes through the detailed implementation. And there's a lot of really good value that explores how you go through and do division and square root with floating point. And then we have bit manipulation and the cryptography extension. We discuss how you do privilege modes through supervisor and user mode, and CSRs, fence, and counters, virtual memory, memory protection, and so many more other architectural extensions. It is basically specified in the RISC-V spec. There's a configuration parameter for this. And Wally allows you to turn on and off all of these, and if there's a parameterizable option for it, there's a way to make that change, or to set that configuration. But there's also microarchitecture features that you can play around with inside Wally. For example, there's instruction and data caches, and you can control the specific parameters, such as the way size, the number of ways, the cache line length, the replacement policy. The branch predictors allow you to have different types of branch predictor. You can do 2-bit saturating counter, G-share, local history predictor. We have branch target buffer, return address stack. We have vectored interrupts. And then we have a number of standard peripherals that are supported, such as the core local interrupt controller, the CLINT, the platform local interrupt controller, the PLIC, UART, general purpose in and out, SPI, and tightly integrated memories. So before I continue, are there any interesting questions out there? I guess maybe, should we save the questions for the end, maybe?
Yeah,
so
there are some questions popping up, Rose, but let's leave them till the end.
Okay. Okay, so that's the description of what Wally is capable of and all the different configurations, but we also have to prove that the hardware can actually operate correctly, and that's what verification is for. So Wally has a number of different verification suites, the most important of which is the ATC functional coverage tests. These were developed in collaboration with several universities, Habib University and UET, with collaborations with 10x engineers. So this was Harvey Mudd, those two universities, and 10x engineers. And one of the things that we leveraged in the process was Imparis DB. So Imparis is a lockstep and compare tool. So as Wally commits its instructions, all of the architecture state that it changes is sent over to Imparis DB. Imparis DB is what's called a reference model. And so the Imparis DB compares the state changes between the two models, between Wally and its own model of what a RISC-V processor should be, and says, do these two changes, does this state update make sense? And if it doesn't, then it stops the simulation and reports that there's an error. So it's been an extremely valuable tool for rapid debugging. But we also have less aggressive and sophisticated testing in case we don't have access to Imparis DB, such as memory-based signature testing and tons of our own custom testing that is specifically targeted towards the privileged instruction set, virtual memory, and privilege tests. So this is our textbook. It has there's 4 authors: David Harris, my PhD advisor, James Stein, myself, and Sarah Harris. The contents of the textbook are very vast. It's divided really into two pieces, the physical textbook and the PDF editions. So to manage, we wanted the book to be affordable for students because we understand that textbooks are expensive. And so this was a compromise decision that we made. And to keep costs low, we kept the most important core material in the physical textbook, and the full PDF version has additional content in it. So it has the last 4 chapters and the 5 appendices. So in the physical textbook, you will get a history of computers. So this is everything from back to before the development of a transistor, all the way up to modern computer history. And then we go into what is RISC-V? How did it begin, and where are we now? And then we have RISC-V tools. So this is everything from compilers to verification tools. And then we have HDL practices. So this is system Verilog paradigms that are known to produce good hardware. And then we have design verification. So we have an entire chapter that's dedicated to how you go about writing test plans and evaluating your hardware to make sure it functions correctly. And then we have an entire chapter that's dedicated to the synthesis results for Wally. It also teaches how you set up synthesis, how you interpret the results. And then from there, the rest of the chapters are all about the design of Wally. So the first chapter is your intro to the pipeline fork. So this builds up a RV32I or RV64I. So this is your basic integer instruction set. And from there, we add the privileged instructions. And from then, we add bus interfaces. So we add the AHB bus interface. So now we can talk to external memories, external peripherals if we have them. And from there, we add in our caches. So this is one of the first really complicated chapters. And then we add in virtual memory with the memory management unit. And then we integrate the caches and the virtual and the MMU together in the load store unit. And in chapter 13, we do the same thing, but for the instruction fetch unit, and we add in branch prediction. In chapter 14, we modify the LSU, the instruction fetch unit and the decoder to add support for compressed instructions. And then the remaining chapters are all about adding support for additional instructions. So, or the next couple chapters are about adding support for additional instructions. So we add support for the M extensions, for integer, multiply, and divide, and then floating point. This is the really big chapter or chapters. So chapter 16 and appendix F are paired together. This will give you a really comprehensive experience to understanding how floating point works and how to implement it. And then we have the atomic chapter for understanding how to do AMO operations and load, reserved, store, conditional. And then we have bit manipulation in crypto, and then a whole bunch of ancillary extensions. In the PDF, you'll also get peripherals, so you'll get SPI, you'll get UART and the Clint and the PLIC definitions and implementation. And then also you'll get benchmarking results where we go over CoreMark and MBench. And in chapter 20, we'll show how we implemented a Linux build root to be able to simulate in both QEMU and in RTL simulation. And then in the FPGA chapter, we bring up several different FPGA boards on Wally and boot Linux. And then the remaining appendices are various helpful guides or synopses of the textbook. So we have the Wally synopsis, which is just a collection of results and figures throughout the textbook. Linux guide, so helpful hints on useful commands about Linux. A Git guide, so if you're unfamiliar with how to use Git, because our repository is in Git, this can help you get started in understanding the Git principles. The Tickle handbook, so a lot of the scripts for synthesis and to control QuestaSim use Tickle. So this can be helpful guides for those things. So one of the things we try to do in our textbook is illustrate complex designs in System Verilog. So we chose to use System Verilog because it's an industry standard industry standard hardware description language. And we could have picked another language such as Chisel. And the primary reason we chose not to is we didn't want to have hide the abstraction layer. We wanted to keep a closer relationship between what students are learning and describing in hardware, whereas Chisel hides some of that abstraction or creates a greater abstraction layer between what students are learning and what they're creating in terms of hardware. It also is easy to create efficient synthesis with System Verilog, and the coding paradigms that we present in the textbook allow for nice one-to-one representation between this specific coding style and generating a specific piece of hardware. And finally, the main thing here we want to do is we want to connect theory of what is this concept in computer architecture to a specific implementation. And we try to do that in every chapter. So our conclusions from this. So our real goal here is we want to bridge that gap between theory and implementation. And we hope that this book is going to serve as that platform to bridging that gap. This is a processor that is extensively documented with detailed descriptions and figures for every single part of the design. nearly every module or every major module within the system has a detailed diagram for the processor. And importantly, it supports many of those advanced architecture extensions and features, making it useful for so many different applications. It's not just a little toy processor. All right, well, that ends the presentation. I think we can take questions now.
Yeah, good job. I'll start off with the questions. We're getting a couple of questions in the Q&A, and I'd encourage people as we're talking to continue to enter them there. Before we get into those Q&A though, I got a couple of questions I want to pop off, and we want to get to there's two of them that everybody needs answers to. And the first is the authors listed here: David Harris, James Stein, Rose Thompson, Sarah Harris. So two questions. Is it just a coincidence that David and Sarah Harris are co-authors?
Not just this, but today with this webinar, it's great to have you, Mike. We have Thompson, Thompson, Harris, Harris, and Stein.
Yeah, I was gonna mention that we got a lot of Harrises, we got a lot of Thompsons. I want to clear things up. As far as I'm aware, and trust me, I would claim her as family if I could. But as far as I'm aware, Rose, we're not related. Is that a fair statement?
That's as far as I know as well. I don't think we're related.
Yeah, well, I mean, there's some questionable heritage in my family. There's some debate that goes back a few years ago about who my great grandfather really was, but I'll just leave it at that. So there's a chance. There's a chance. David, how about you and Sarah? Are you related in any way?
We are not related, except that my master's advisor at MIT, Bill Daly, was Sarah's PhD advisor at Stanford. And then Sarah came and taught at Harvey Mudd for a number of years, and we began writing books together. Her husband got tenure at UNLV, and she eventually left Harvey Mudd, unfortunately, to reduce the commute, go to UNLV. But we continue to have a wonderful collaboration. She's a tremendous author and editor, and amazing attention to detail.
I can attest to that, absolutely. So the other one is, and this I get more questions about this. You would not believe it. I'm not making this up. When people ask me about Wally, this is the second question I get every time. What's up with the funky artwork?
So Sarah Harris did the cover art. So that is an original drawing from the author team. And it was inspired, there's a name for this form of art, but it's the Where's Wally kind of kids books, which we did not actually mention in the text because of concerns of copyright. But there's a PDF, I think, on the book webpage that lists what all of the cover is a bit of a puzzle and a bunch of visual puns. You go to the bank to get $, cash. The multiply unit is a maternity hospital. Divide unit is divorce lawyers, and so forth.
I got a few of the jokes, but I didn't get that divorce lawyer.
Yes. So you can try to figure out as many puns as you can, and then check for that PDF to see what else is in there. But we enjoyed the art style and enjoyed Sarah's art.
Okay.
Also, all four of the authors are on the front cover.
Well, I will say David comes out right away. I'll look for the other three. This is a question for you, David. You and Sarah are famous for co-authoring a couple of textbooks related to computer architecture. The latest one is actually a discussion of computer architecture based on RISC-V. So why then did the world need another textbook based on the computer architecture of RISC-V? What does this textbook fulfill that the previous one did not?
Right. So Sarah and I have been writing introductory textbooks targeting a first undergraduate course on computer architecture and digital design since 2006 or so. It's gone through 4 editions, 2 MIPS editions, an ARM edition, and a RISC-V edition. This book is a different level course. It would be an intermediate to advanced course. And there are wonderful books in the field. Hennessy and Patterson's Computer Architecture is a classic that we've enjoyed for a long time. It's what got me into the field in the first place. Actually, the first edition of Hennessy and Patterson, I'll go on a little aside here. When I was an undergraduate, my parents asked me what day I wanted to fly home from finals from Boston to California, and I was too lazy to look up the final schedule for my courses, so I just told them, buy me a ticket back on the last day and I'll be fine. And it turned out that all of my finals were on the first 2 days, and same with my friends. And by the end of the week, there was nobody left in the dorm, and there was a blizzard going on. And I walked across campus to the bookstore. My parents were kind enough to get me an account for the bookstore where I could buy a book for myself each semester. And I picked up first edition of Computer Architecture, read it cover to cover that day in my dorm room. It was a manifesto saying how to build computers, saying all of the judging computers based on the elegance of their architecture was wrong, and we should base them on performance. And it was the beginning of the RISC revolution. And I've been doing this stuff ever since. It's such a well-written book. But that book really focuses on principles. And Rose and I are microarchitects at heart. We like designing physical structures that implement these architectures. And we wanted to have a book that brought together the principles and the implementations, and particularly rested in the context of RISC-V and the practices that people going in industry would need.
Cool. That's quite the story. I do think that textbook changed the lives of a lot of people in this industry. That is definitely true. I suspect that this one will have a similar effect.
We've never seen a book done in this style of having all of these implementations, and we're trying to figure out why. First reason we've learned is it took 5 years to write this book. My hardest books in the past have been 2-year undertakings.
Wow.
And so it just was a ton of work to get the RTL right and verified and get all these diagrams drawn. Rose drew many of the hardest ones. We're also torn. It could be illuminating of all of this detail of how things actually work, or it could be gratuitous detail and make the book incredibly boring. And I think we'll get feedback from our readers of who likes it and where they are in their career. But we tried to write things that we thought we would have liked when we were at this stage in our career of trying to understand how it all goes together.
We have similar conversations within the OpenHW Foundation amongst the staff about exactly that question, all those questions that you bring up. I'm on record as stating that the advent of this textbook will make the CORE-V Wally, the CVW repository, our most popular core. Time will tell. It's up against some pretty tall competition because there's a number of very popular RISC-V cores that OpenHW curates that have been around for quite a long time and have quite a what phrase will I use? Loyal fan base is not really an appropriate term. It's more of large and loyal adopters, a population of adopters. But Wally is unique in that it implements an open standard. The source code is all open source, and there's a textbook now that explains why the architects and developers made certain choices. Like, why did you choose a branch predictor like this? Why did you do that? Those kinds of discussions, I think, will just drive an awful lot of eyeballs to this thing, and inevitably people will start spinning out silicon. So I'm not picking favorites, but I do as a hobby like to pick technologies that will be a winner. I think this one is feels that. I'd like to move on to some of the Q&A is popping up quite a lot here, so I'm gonna switch over to the Q&A that's coming in. The first question that came in, and I'm looking for it here because my Q&A bar reorders things. Here we go. This is a low-level in the mud question that you can probably answer off the top of your head, or at least I hope. It's from Ritu, and the question is: the reg file logic in the IEU and the FPU is triggered on the negative edge of the clock. Is that intentional?
So it was at the time this was first written in 2020. It goes against the way we've done all the rest of the logic, and I'd have to revisit the path that interfaced to the reg file. Rez, do you happen to know off the top of your head?
I thought the write into the reg file is written on the negative edge, and the read path is asynchronous.
Yes, it is.
Yes. Yeah, that's correct. I cheated. I looked at the code while you guys were talking. Anyway.
It's a good question. It's worth revisiting.
Yeah. Here, I've got a suggestion for you, Ritu. If you have a question about a piece of open source IP that you find on GitHub, I encourage people to open an issue and just ask the question there. That is the beauty of open source, is that you have access not only to the source code, but you've got access to the community of people that are developing that IP, and that's a tremendous thing, and it becomes a good way to get involved with that community. So I'd recommend there. Let's just look for another couple of questions. This one is from Dishesh. I hope I'm pronouncing the name properly. Rose, you mentioned that Wally supports many advanced architecture extension and bridges the gap between theory and implementation. How straightforward is it for a user or a student to integrate their own custom instructions into the Wally framework? And does the documentation provide a process for this?
So we don't provide documentation in the textbook to explain how you would go about doing custom instruction. In fact, there's nothing in the textbook that talks about the, so for example, there's the custom instruction interface that some of the other OpenHW Foundation cores implement. So Wally doesn't implement that. That's actually something I'm interested in adding to Wally in a future version. But that's not documented.
Fair enough.
Now, in terms of how hard it would be to add, if you're wanting to modify the decoder, it's honestly not that hard to do, but you would need to become familiar with how we go about modifying the instruction decoder.
Yeah, and the RISC-V standard makes it relatively straightforward to add custom instructions, and I think that tends to attract a lot of people. But as soon as you create a decoder in RTL, changing the instruction set or adding your custom instructions, now you're actually opening up the decoder, opening up the pipeline. So I'm going to offer an opinion here on the question. My first question, my response to the question would be: have you considered why you're interested in creating a custom instruction? The RISC-V ISA is very rich. supports a lot of instructions, and the value of a new instruction has to be very high in order to justify the cost of actually implementing it. And it's not just the RTL. As soon as you create a new instruction, now you've got to create software to support that instruction. So that means you need an assembler. That means you need a compiler. Now you've got applications now you need to write application code that would use that feature. That adds an enormous amount of complexity. Sometimes it's justified. Sometimes it makes sense to add a custom instruction, but I would really encourage people who are excited about adding custom instructions to really think about why they want to do that before they go to that effort, because it's not trivial, and it's not the problem only gets bigger when you solve the RTL problem, when you implement the instruction and get it to work and not break the core that you've already got working. Now the real work begins. It's really hard to support custom instructions. And in case you're wondering, yes, this is the voice of bitter experience.
I can actually give you a concrete example. I'll have to hide the company involved in this, but there's a company that was looking at modifying Wally to add a custom dot product instruction. And I asked them, why are you doing that? Do you need a custom dot product instruction when you could add vector support or a subset of vector? And they came back and realized, oh, you know what, vector is actually a better fit for the application overall, because vector has not just the ability to implement dot product through the vast integer, the vast array of vector integer instructions.
Oops, looks like we lost Rose.
Maybe she's frozen. I'm still alive. And she's and her connection's bad.
Okay. Well,
Am I back on?
yeah, you sound like you're back on. That's great. We lost you for a few moments.
Oh, where did I cut off?
You were just explaining that the organization you were dealing with, you had persuaded them to look at the vector ISA rather than implement their own dot product ISA.
Yeah, so I asked them to look at vector, and their conclusion from that was not only was vector able to provide the same functionality as the dot product, but is able to vectorize other code in the application. We got a faster implementation of their algorithm using the vector ISA if they had implemented their own dot product instruction.
Yeah, and I think that would be a common experience, particularly now. The RISC-V ISA, there's a lot of instruction sets. It's got a very rich instruction set. Generally speaking, someone has solved the problem that you're trying to solve. So just follow that. Here's a question that I find pretty interesting. Is there an online public forum for readers of the textbook to discuss various aspects amongst themselves?
Oh, right now all we have is the GitHub. That's an interesting idea, though. Yeah.
One of the other open hardware projects, I'll just throw the name out there. It's CORE-V by EI Nico. They have a very, very popular Discord channel that discusses various aspects of their core. There might be a Discord channel to discuss the RISC-V System-on-Chip Design textbook. Might be an interesting one.
Thanks.
Here's one I'll toss to you, David. The lockstep verification flow currently depends on ImperisDV, which is a proprietary tool. Is there an open source lockstep implementation available? And if not, what might be blocking it?
Maybe Rose would best talk to that.
All right.
So Sail is, I'm less familiar with Sail's lockstep and capabilities. The last time I looked at it was over a year ago. I know it wasn't quite as much as ImperisDB at the time, and when we were setting up ImperisDB, it was over 4 years ago now. That feature wasn't even available with Sail. I suspect, but I do not know for sure, that we probably could use Sail in a robust capacity than ImperisDB. But I would need to reevaluate it all at this point. But that's speculation on my part.
ImperisDB is a wonderful tool. It's a very robust, tested widely in industry, and has been used on many very sophisticated machines. I think open source tools will evolve here. That's not what we're trying to solve with this book. And most of this book does use open source flows, but we also take advantage of commercial flows where it's appropriate to get non-core capabilities like this.
Yeah. We've had a really good relationship with Imperis, now Synopsys, and it's been a very good collaboration effort with them, and we would love to keep relationship with them alive.
Yeah, I definitely agree that the ImperisDB reference model. First of all, it's a true reference model. It was created to be a reference model. The other offerings that people mentioned, Spike, Sail, Whisper, these were developed as instruction set simulators, not necessarily reference models, and certainly not a reference model that would run in lockstep with the design under test. Internally, we are toying with this topic as a future webinar from the OpenHW Foundation. So not going to make a commitment to it, but it is something we're talking about. It's a deep topic with a lot of layers to the onion, so we'll just leave it at that. Here's a question that I like. I'm the verification guy at the OpenHW Foundation, so I really like this question, and I suspect it's for Rose, but I'll let either David or Rose handle it. As RISC-V becomes increasingly heterogeneous, what do you think is the biggest verification challenge facing a RISC-V design? Is it the core itself, the interaction with other cores in a multi-heart system, interaction with the memory interconnect? What do you see as the biggest verification challenge in a RISC-V SoC?
It's hard to quantify what the biggest challenge would be. There could be multiple very challenging things the moment you hop into the space of multi-core and large SoC systems. There are many things that can interact in complex ways that are hard to predict. When you have a single core system, DB is so much more deterministic. But once you go to 2, 4, 8 or more, right, you have a much more complicated time of understanding what's going to happen inside, and understanding the complex cache interactions, the ways in which you might interlock your bus in deadlock or live lock. Those are things that get tough. And for me personally, I haven't gone down that path in verification, so I'm not an expert in that area.
I would say, based on our experience working with the RISC-V Certification Steering Committee, that there are a few thousand rules, normative rules, in the RISC-V spec that can be tested with order of millions of tests that can run in minutes on a reasonably powerful server against a simulator like Spike or Whisper. So certifying that single core is relatively easy. On the other hand, checking, for instance, for memory, the memory rules, the litmus tests can run for weeks in silicon and still empirically find new bugs after multiple weeks of running. And so that's at least 6 orders of magnitude more compute than testing normative rules on a single core. Also, when you bring in the IP, RISC-V has ballpark of 1,000 pages of spec, while each of the IPs you bring in, DDR, Ethernet, PCI, commonly have specs of similar complexity. And there are many, many of these external devices hooking up to a server.
Yeah, absolutely. There's a couple of short questions here. I can handle this one. It says, do we need proprietary or licensed tools to work on the textbook exercises? The answer is no. As Dr. Harrison and Thompson were saying, the ImperisDV, if you want to use ImperisDV, that's a licensed product. DCS and Questasim, there's lots of scripts for both of those in the textbook, and those are licensed tools. But you can also use Verilator, I think, for all of it, excluding ImperisDV. And Verilator is a free and open source system Verilog simulator that's not fully complete, but quite complete. And I believe, correct me if I'm wrong, folks, but complete enough for most of the textbook examples.
Coverage, code coverage, and functional coverage are just coming into play, but yes, everything we're simulating the core is robust.
Great. Yeah. Here's one. I love this one. Any plans to support an out-of-order execution pipeline in Volume 2?
We have a team looking at the superscalar implementation this year. Nothing in the near term on out of order. It would certainly be interesting. As the longer I've looked at this, the more concerned I am about the pedagogy, that all the details necessary to make out of order work, when crossed with all the details necessary to make virtual memory and caches and privilege and branch prediction and everything else work, may lead to a machine that's so hairy that it defeats the pedagogical purposes.
Yeah, I will say, as a verification person, the processor feature I fear the most is out of order execution. It is it's a target-rich field, and it's really hard to get all the corner cases, but also fascinating. Really a challenge, really an interesting problem. Let's see what else we got. Here's one. Once again, as a verification guy, I am just so excited that this textbook actually talks about this. I believe that the textbook answers this, but the question is, what would the technical readiness level for the Wally core be, and how do you think this would evolve in the near future?
Well, first of all, we are indebted to you, Mike. We came into this with antiquated verification experience, and you have been our mentor in so much of this and have connected us with so many good people. The OpenHW Foundation has such a good organization and I think its greatest strength is bringing together wonderful people. And thank you for what you've done on that and what you've taught us and the people who you've introduced us to who've taught us things.
I'm going to start crying, David.
Open is an amazing place and a joy to be in.
Oh, thank you.
We are at technology readiness level 4. We are very close to 5. It needs we need 100% code coverage, 100% functional coverage, and no open issues. At this point, let's see, code coverage was 100% the last time I looked. Functional coverage, I believe everything known on our test plans has been done, but we're gradually adding things here and there. And there are 2 open bugs that I believe that are juicy ones. Does that sound right, Rez?
I believe it sounds like that. Yeah, the open bugs are pretty interesting, and it's just a matter of time before they're finally closed.
So technology readiness level 5 is the goal.
Cool. I'll share a little story about you with everybody about technology readiness level 4. Rick O'Connor, who was the first CEO and the founder of the OpenHW Foundation, then called the Open Hardware Group, the way he described TRL5 is like this. You would walk into your director's office, slap your badge on their desk and say, I bet my job that this IP can be synthesized and implemented in an ASIC, and there will be no service affecting bugs in the design. That's what TRL5 means. That's a very high bar. There was a little bit of a weasel word in there. The weasel word is no service affecting bugs, not no bugs, but nothing that would prevent you from selling the device and from your customers being able to use it in production. That's a very high bar. And I'm super excited that the Wally team is shooting for that.
I don't read it quite that high. We've been developing the certification tests, and mature open hardware cores are finding bugs. Commercial cores are finding bugs. They may be questionable of whether they're surface affecting, but there are certainly violations of the spec.
Absolutely.
I don't believe anything is ever fully debugged, but
nothing is ever fully debugged. Every now and then, somebody who's typically selling a verification tool will tell you that their tool can find all the bugs. You can just send those people packing, because there's no way you're ever going to find all the bugs in anything. It's just a question of, can we live with the bugs?
Being ready to ship silicon is what we hope for.
Well, I think Wally is, if not ready for that, is well on its way for that. It's a very, very robust, very stable, very well verified core. Like I say, I'm the verification guy, so I really appreciate that. Speaking of verification, what were some of the biggest challenges you faced from an architecture definition and a verification perspective? Like when you were putting this together, were you conscious of any decisions you were making to, specifically address complexity of design or complexity of verification?
Oh, before we had in Paris DV, debugging was actually pretty challenging. I remember this is not design related, but is very much debug related. I remember we were putting the FPGA together, and there were still a lot of bugs, and we were using this is not a core bug. This was a bug ECU 118 board. The UART2 USB chip on that board is not programmed correctly, and it's configured in a loopback mode, but I didn't know that when I was setting up the board. And the UART controller that we were building was also very, and so the interactions between these two sets of bugs, I spent several months trying to just get anything to communicate, and it was a real big struggle. And if we had had Impairs DV before that, before I had gotten to that point in time, we would have found so many more bugs because I was tripping over so many other core level bugs to get to that. It would just have been so much easier. The specific bug that really tripped me up was the little chip that did the UART to USB conversion was configured in loopback. So when the Linux kernel transmitted would do a K print out, it would loop back the data. So anytime it would print out data, it would just loop back, and it was configured in a mode that was the same baud rate as the expected terminal. So it would just print out random garbage to the screen. It was really confusing.
We've all been there.
Was,
and a good debug tool is great. There's several more questions to get to, but unfortunately, I'm conscious of everybody's time, and we're coming up on the top of the hour, and Ludmila still has to run the draw. So what we'll do is we'll capture all the questions, and we'll post an answer to them in one of the Open Hardware forums, and we'll give everybody a link to that. Thank everybody for all the questions. It's great when there's more questions than we have time to answer. And now I'm going to turn things over to Ludmila, who's gonna answer the question: who gets the textbook?
Hi, thank you so much for that amazing presentation. Thank you all that stayed until here to see who is the winner of the textbook. I'll share my screen really quickly. I already uploaded all the names. Okay, so we will run the raffle now. I just put the last names, and okay, good luck. Sorry, there's.
If the name Thompson comes up, she's already got one.
Ashraf, are you there? Let me find your name. Just a moment. Ashraf Adel, are you there? Okay, we will contact you by email asking for your details so we can send your prize. Okay, thank you so much. Thank you, all of you. Thank you. All right. You are the winner. Thank you so much, everyone. And I hope, oh yeah, okay, you're there. Nice.
He's there. Excellent. Congratulations.
All right.
Perfect.
Thank you all.
All right.
Thank you for hosting this.
Thank you.
Dr. Harris, Dr. Thompson, thank you very much. Thank you very much for Wally. Thank you for the textbook. And thank you for participating in this webinar. I really appreciate it. We'll see you soon.
Thank you. Cheers.